In this video, I'll be introducing manifolds with boundary. So let's think back to a manifold. So let's look at the example of the circle. Now this circle, just the line on the outside of this circle, is a one-dimensional manifold. But what if I give it all the space in between? Okay, so not only do I have this circle outside, I also have all of this inside. This is what's known as B2, except I include that outside, so I put a bar over it. So this is not an open ball, it's a closed ball. But this outside is what really bugs me, okay? Because if I have a point on this outside, then no matter how small my interval is around it, no matter how small it is around it, I still have this closed part of it. So on this boundary, I can't make this an open set. I have to make it like half open, half closed. It's like right there, close to being open. No matter what open interval I take around it, there's still this closed part. And so this is what a manifold with boundary is. It's a manifold, but you can allow it to have a boundary, like this. You can allow it to have a closure. Note that sometimes when I say that there's an open set in a manifold, and then that it isn't open because there's a little closed part, what I mean is that it's not going to be open when you map it into the real numbers. It can't be homeomorphically mapped to an open set in the real numbers. We defined, okay, so a manifold with boundary is going to be a space M such that 1, for every point in M, there exists an open U, a subset of M, that U contains X, so, and a homeomorphism phi, that brings you from U into, now get this, it's going to be U hat still, but it's not going to be a subset of Rn, it's going to be a subset of the half plane. Okay, now the half plane right here is going to be the set of X such that X is in Rn and X1 is bigger than or equal to 0. So if I have R2, I just exclude the bottom half, but I include that x-axis right there. So intuitively, right here is like the boundary. It's like the boundary of the half. No matter what open interval I put around it, it still has just this line right here, which is closed, makes it not open. That's why we make it an open subset of the half plane instead of the entire plane. Okay, 2 and 3 are the same as manifolds. Okay, so they're just the Hausdorff condition and countable basis. This is the important part. We change what space it maps into so that it can have a boundary. And so now, a new definition is going to be the interior and boundary of a manifold with boundary. Okay, so suppose X is in the manifold, or the manifold with boundary, and X is in some chart U phi. We say that X is an interior point if phi of X, if its representation is not an element of the x-axis. And the x-axis is the set of X such that X is in Rn and X1 is equal to 0. What does this mean? Well, it means that if we have this half plane right here, and I have my manifold with boundary right here, and I have my point X right here, and an open set around it, I map it down via phi into here, and it doesn't land on the x-axis. It doesn't land there, it doesn't land on the boundary that I was saying. The reason why we had it was because I needed a boundary, and it doesn't land on that. So that means that it's not a boundary point and it's on the interior. And so a boundary point, as you might have guessed, is where phi of X is an element of that set. Okay, so for example, if I had this point right here, its open set wouldn't be entirely within the realm of being mapped down to R itself homeomorphically, but it can be mapped down to this half plane homeomorphically because there's this edge right here. Okay, so what we do is we say that M with a little degree sign is going to be the set of interior points. And this is called the interior of M, and we say del M, that's a del like the partial derivative, is going to be the set of boundary points. So that's how you define the interior and boundary of a manifold with boundary. Okay, and now you're saying, what's another example? I don't really see how this is really that important. Well, another important example is the Mobius strip. You've probably seen this all over the place. It's actually not a manifold. It's actually a manifold with boundary. Okay, so a Mobius strip is where I have this square, and what I do is I take this side and I flip it around in 3D space so that it matches up with the arrow on that side. Here's an animation that could help you visualize it. Here you see the rectangle. These blue lines are going to be the boundary of the Mobius strip, and these two white edges right here on this rectangle are going to be what I'm connecting to make the Mobius strip. So let's go ahead and connect these while making a twist to make a Mobius strip. Okay, so I'm beginning to twist it around like that. You can see the twisting happening there until I finally connect it and get this Mobius strip. You can see that the blue edges are going to be the boundary of this manifold. So this is not a normal manifold. It's a manifold with boundary because it includes these blue edges. Okay, so really quickly, what I have to tell you is that the interior of M union the boundary of M is equal to M. Okay, that's not too surprising. Obviously it is. But the important part is that M, the interior of M, intersect the boundary of M is the empty set. I'll leave that to you to prove it. If you guys want to prove it, type your answers in the comments. Maybe make a latex PDF. I'll pin whoever's right. Okay, what are the properties of manifolds with boundaries? You'd imagine that they'd have some pretty interesting properties. Well, here's a theorem. Theorem 2 is that it has 3 parts. Part 1 is that M with the interior of M is an n-dimensional manifold. Here, of course, n is the dimension of M without boundary. Okay, so it's an n-dimensional manifold without boundary. 2 is that the boundary of M is an n-1 dimensional manifold without boundary. Okay, so for instance, in that ball I had here, okay, there's the interior right here, and then there's also the boundary. The boundary is a circle, that's a 1-dimensional manifold. This is a 2-dimensional manifold. And that's what this theorem is saying just in general. So for example, if I look at the torus again, so the blue edges right here, if I remove them and I just have the blue edges, this right here is just the blue edges of the manifold, and these create a 1-dimensional manifold in 3 space because it's just a curve. And this right here is just the Mobius strip without its boundary. This is, in fact, a manifold. It's not anything else, it's just a manifold because I removed the blue boundary. And number 3 is that M is a manifold if and only if the boundary of M is empty. So if it doesn't have a boundary, then it's a manifold, and if it is a manifold, it doesn't have a boundary. That's super easy to prove. And that's it. And I'll leave it to you to prove. Again, if you want to write your answers in the comments, I'll pin whoever's correct. what about the topological properties of manifolds with boundaries? Well, again, another theorem, but this one's really easy because we just did it before practically, is that
N has a basis of pre-coordinate balls. Okay, number 2 is that N is locally compact. Number 3 is that N is paracompact. And that N is locally path connected. And of course, N has countable connected components, which are path connected components.
basically all the things we did last time. Just the same with manifolds with boundaries. Manifolds with boundaries have all the same properties, topological properties, as manifolds without boundaries, and their interior and boundaries are manifolds themselves. So that's really nice. And that's it.